Once again, let me continue with bearing capacity of shallow foundation, and in the previous lecture I have tried to show the impact of water table on bearing capacity, where I have shown that if the water table is a significantly great depth, that means not within the shear zone, then whatever bearing capacity we get, and if it comes by some means to the surface, then it water bearing capacity becomes just almost half. So, that is the quite noticeable difference. So, one has to keep that in mind, that while designing the foundation, that the variation of water table, that means throughout the year what is the worst possible location of water table has to be considered, and accordingly bearing capacity should be considered. Otherwise, if you estimate the bearing capacity considering ignoring the water table, and finally water table sometimes comes to the surface of the footing, and then in that case water bearing capacity will be significantly reduced, and that may result in your failure sometime. Of course, we used to keep we keep generally significantly large value of factor of safety, because of that sometimes it may be safe, but still we need to keep a sufficient margin of safety, and to make sure that one has to consider the water table effect, and how to consider that I have shown in the previous lecture. And now I will try to show various terminologies we use in bearing capacity theories, and let me go to the slide that, and let me see that various terms that we use, actually that is one, sometimes we call gross bearing capacity, sometimes we can say net bearing capacity, net ultimate, net shape, and then allowable or shape bearing capacity. There are different terms, and if there is a suppose if there is a ground surface somewhere here, and finally if you dig and finally place a foundation somewhere here, then here this footing will impart some pressure on the soil here through this footing, and that pressure actually will be nothing but the gross pressure. That means, because of this soil over here, the structural load and the self weight of the footing and column all together, whatever is giving on this soil, that is actually gross pressure. Okay. So, the gross Q g is the gross pressure at the base of the footing due to the weight of the superstructure, self weight of the footing, and the weight of the soil fill over the footing. So, that is the one. Now, if this pressure is slowly increases, then finally what will happen? Soil will fail, and that actually when it fails, then that will be actually gross ultimate. So, Q u sometime we can write Q u as actually ultimate, but that can be considered as gross ultimate. So, gross ultimate. So, Q u I just take as gross ultimate, and in that case that is one definition. That means gross pressure, and then if you subtract this that soil weight from here, then that become net pressure. And if I now consider as Q u as a gross ultimate, then similarly net ultimate I can visualize net ultimate. So, at this point this is the ground surface, at this level what is the bearing capacity, ultimate bearing capacity, that I suppose Q u, then similarly at this level I can find out Q net u, that means net ultimate, and net ultimate is how? Q ultimate minus, because of the soil weight has to be subtracted, soil weight to be subtracted, and from there I get net ultimate. And ultimate pressure actually is the pressure at that point actually failure may occur. Okay. So, because of that we never go up to the ultimate pressure. So, we how much we go, actually we used to go, we can go up to shape load, shape pressure. So, then if we introduce a factor of safety on this, then QNS means net shape pressure. So, Q net shape, that means QNS, how to find out? QNU divided by a suitable factor of safety, then I will get Q NS, that means net shape pressure. So, that is nothing but QNU by Fs, and now QS, that means Q shape or Q allowable final will be QNS plus gamma dF, because that much pressure can be added, because there is no need to apply what factor of safety. So, in the net pressure I have applied factor of safety, but this gamma dF is known. So, because of that there is no need to apply factor of safety, directly you can add. So, ultimately allowable pressure which can be obtained by Q net factor net U by factor of safety plus gamma dF. So, that means there are number of things can be there, but you have to understand what is what. One is actually gross and one is net. Gross is what you are applying total, and if you subtract the surcharge, that means from the base of the footing to the surface, whatever the soil weight if you subtract, then that become net pressure. And similarly, now I can find out at any depth ultimate pressure, and I can find out net ultimate pressure. So, ultimate pressure actually how to find out? I can apply bearing capacity theory, and then I will get QU, and then if I subtract surcharge, that gamma times dF, then I will get Q net ultimate. Okay. And now, if I want to find out Q net safe, that means how much safe net pressure. So, then I have to apply a factor of safety, and finally, if I want to find out what is the safe allowable pressure, then Q net safe plus surcharge. Okay. So, ultimately that much, that means whatever allowable pressure we are considering at a while designing the foundation, allowable bearing capacity means whatever pressure, that means pressure of foundation, superstructure and everything together with the water soil pressure, everything together is the bearing capacity. So, because of that ultimately by calculating net shape, I can add this gamma dF to get the allowable pressure or shape bearing capacity of the soil. So, these are the few terminologies to be remembered in while doing this calculation, and I will try to show by this by showing an example. You can see that in this problem a column footing of 1.8 meter by 1 meter, 1.8 meter by 1.8 meter is buried 1.5 meter below the ground surface in a dense cohesionless soil. That buried means what? The depth of the foundation is 1.5 meter, that means it is something like this, footing is something like this and ground surface is this, and that means this depth is 1.5 meter and this width is 1.8 meter, and this is the soil is dense cohesionless soil, that means C is 0 and phi is having value of 36 degrees, and unit weight gamma actually is 21 kilonewton per meter cube, and determine the allowable bearing capacity of the footing assuming a factor of safety of 3, and groundwater table was not encountered during the subsurface soil exploration. That means, we can consider that we generally while design the foundation or constructing the foundation, we generally carry out the subsurface exploration investigation, and while doing that we go sufficiently depth, the sufficiently great depth to find out the layering and all those things, and that in this problem it is mentioned that during subsurface investigation the water table was not encountered. That means, even we go at certain depth which is significantly deep, there also you have not seen water table. That means, water table effect can be ignored, and if you ignore that, then I have to find out now what is that determine the allowable bearing capacity. Allowable bearing capacity, I have defined there are so many, that means ultimate bearing capacity, then net ultimate bearing capacity, then net shape bearing capacity, then I have defined allowable bearing capacity of or shape bearing capacity. So, that means it is asked the last part, the last one is asked. So, you have to, that means I have to calculate one by one all step and finally go to the last step. So, let me go to the next slide and do that step by step. And so, I will show the footing first. The footing is somewhere here and your df equal to 1.5 meter and b is b equal to 1.8 meter and phi equal to 36 degree. From there actually I get NC equal to 63.53, NQ equal to 47.12, that is coming, that will come from table, and N gamma will be equal to 54.36. So, and water table is not there. So, Q ultimate I will calculate, Q ultimate will be equal to C N C plus gamma df N Q plus half gamma B N gamma. So, C is 0. So, this part will become 0 plus gamma is actually here is given something, gamma is given 21, and so 21 multiplied by depth is 1.5 multiplied by NQ is 47.12 plus half gamma is here again 21 plus B is 1.8. So, this is multiplied by N gamma is here 54.36. So, Q ultimate or Q u become your 2306. Then I can find out Q N u equal to Q u divided minus gamma times df. So, that means 2306 minus 1.5 multiplied by 21, that will be equal to 2274. And then I can find out Q net shape, that will be equal to Q N u divided by F s. So, how much it comes? 2274 divided by F s is given 3. So, this value comes 758. All are everywhere you have to write unit kilonewton per meter square. This is kilonewton per meter square, kilonewton per meter square. And now, ultimately Q allowable, that means I can write here Q allowable equal to Q net shape plus gamma time df. So, that means equal to 758 plus 1.5 multiplied by 21. So, that gives you 789.7 kilonewton per meter square. So, this is the one, that means I will get first Q ultimate. If there is a water table I could have taken here, there is no water table. If there is a cohesion I could have taken, cohesion is not there. So, I ignored those, only Terzaghi's bearing capacity, ultimate bearing capacity I have used, and from there I got Q u, from Q u I got Q n u, from Q n u I got Q n s, and from Q n s I have got Q allowable, that means this 789.7 kilonewton per meter square. So, this is the first problem I just wanted to explain. Second problem, let me see. Second problem is given something like this: a column footing of 2 meter by 2 meter is buried 1.5 meter below the ground, and similar, that means depth of footing is 1.5 meter. In the dense cohesionless soil, the unit weight of the again 21, phi is again 36, and footing is to carry a total load of 2.2500 kilonewton, including column load and weight of the footing and weight of the soil surcharge. So, total load 2500 kilonewton. Determine the factor of safety against bearing capacity failure, and groundwater table was not encountered due to that means groundwater to be effect of groundwater table to be ignored. So, here actually what I have to do, previous problem actually I have given Q allowable, I have got suppose some 750 or something kilonewton per meter square. So, that means the load capacity of the footing could have been, if the footing size is given. So, suppose 1.8 by 1.8. So, Q of the footing will be 750 multiplied by 1.8 multiplied by 1.8, whatever it comes, that is the Q. Here actually there actually I have calculated the allowable pressure, and from there how much the load can carry by the footing, that I can calculate. But problem here actually is given just reverse, that means all soil properties, footing dimension, everything is given. Now, I have to check what is the factor of safety available. There actually I have already used factor of safety, and from there I got the pressure, and from the pressure if I know the footing size, then I can find out what will be the load carrying capacity of the footing. Here the footing load is given, soil property is given, footing size is given, depth of foundation is given. Now, I have to find out what will be the factor of safety available. If I find the factor of safety is not enough, then I have to redesign, I have to check if load will not change. So, that because of that I have to change the footing size. So, that is the design process. So, I will show this problem. Let me go to the next slide. Let me first draw the footing. Sorry. So, here let me draw the footing first. Footing was something like this. This is 1.5 meter, this is 2 meter, and the Q from here, capital Q is 2500 kilonewton, and phi is given 36 degrees, and when you would given that NC is given, NQ also N gamma, all three will be known. NC value will be 63.53 and NQ is 47.12 and N gamma is 54.36. So, this is there. Now, I can find out from applying bearing capacity equation Q u equal to C N C plus gamma, again same thing, actually it is 21, 1.5 multiplied by 21 multiplied by 47.12 plus half multiplied by gamma is 21 multiplied half gamma b is 2 multiplied by n gamma is 54.36 and this part is 0. So, if I calculate this comes out to be 2397 approximately 2397 kilonewton per meter square. And then your Q net ultimate will become 2397 minus gamma is actually your 21 multiplied by 1.5 and that gives you 2366 kilonewton per meter square. And so, your Q u will become Q u become 2366 multiplied by 2, that gives you actually approximately 9464, and already Q u in the footing is known, and then I can find out factor of safety. Q u is actually 25 your available by demand. So, available actually 9464, this is the factor of safety is capacity by demand. So, that is the available capacity available, and your capacity or available is capacity is means demand is 2500. So, this ratio if I calculate, then it will get factor of safety equal to 3.7, and which is quite large. Generally in foundation engineering, we require a factor of safety at least between 2.5 to 3, and hence it is greater than 3.7, this is safe obviously, and obviously if you want to make little economic, then you can actually this much big footing size is not required. In fact, whatever we have used 2 meter by 2 meter, it may not be required. We can reduce the size little bit and again check the capacity. Otherwise, if we design with this, it will be safe, but may not be economic. So, this is the one step for calculating the factor of safety. That means, what is the available capacity and what is the demand, the ratio is factor of safety. Let me do one more problem, and you can see the last problem. A square footing is proposed to place at a depth of 1.2 meter, twice is not required, on a this depth is not required, on a thick deposit of silty sand, and the column connecting the footing carries a load of 2500 kilonewton. The internal angle of friction phi equal to 30 degrees, cohesion equal to 38.3 kilonewton per meter square, unit weight gamma equal to 18.5 kilonewton per meter cube. Determine the size of the footing using factor of safety equal to 3. So, this is a problem, design problem. Now, the soil is given, soil properties are given, like what is the phi, what is the C, and what is the gamma, unit weight, all those things are given. What is the factor of safety is desired, that is also given, and the footing at what depth it will be placed, that is also approximately given. Footing depth actually from the stability point of view we require. So, 1.2 meter minimum is given, and your what is the footing ultimately connect to the column, and column load, suppose column and footing approximately taking all, maybe load is 25 kilonewton is given. Now, we have to find out the actual size of the footing. So, to do that, the procedure is again similar. Let me go to the next slide and draw the footing first. The footing is something like this, and this is 1.2 meter. Again, water table is ignored, and this is actually square footing of width B not known, and phi equal to 36 degree, gamma equal to is given 18.5, C is given 38.3, and from the phi actually you can find out N C equal to 37 phi equal to 30 degrees, actually phi equal to 30 degrees, N C equal to 37.16, N Q equal to 22.46, and n gamma equal to 19.13. So, these are the things are known. Now, we have to find out ultimate bearing capacity Q u equal to for square footing actually 1.3, C is 38.3, N C is 37.16 plus Q is gamma is actually here 18.5 multiplied by 1.2 and N Q is 22.46 plus half, gamma is again 18.5, B is unknown multiplied by N gamma is 19.13. So, if I simplify this one, then you will get 2349.25 plus 141.56 B. Then I can find out Q net ultimate. Q net ultimate equal to Q ultimate minus gamma df, and if I do that, then you will get 2327.05 plus 141.56 B. Now, if I want to find out footing load actually how it will be done, Q allowable multiplied by B square, is it not. So, how to find out Q allowable? So, this is net ultimate net U. So, this will be I can do 2327.05 plus 141.56 B divided by factor of safety, which is equal to 3. Which is actually 3 plus 1.2 multiplied by 18.5. This become your Q allowable and this multiplied by B square, then this will be equal to footing load, okay. And this footing load has to be equated with what? This has to be equated with 2500 kilonewton. So, this was net ultimate is this, net ultimate by factor of safety plus gamma df is the Q allowable multiplied by the footing area, that gives you the total capacity of the footing, and already applied 2500. So, if I equate these two, then from there I can get the unknown value of B, which is not given, and if I simplify this, then you may get a equation. You can check actually, I may have there is a calculation mistake. So, it will be coming approximately equation, final equation may come something like B cube plus 16.43 B square minus 52.5 equal to 0. So, this equation, if I equate these two, then I will get a equation ultimately B cube plus 16.43 B square minus 52.5 equal to 0. This is the equation I get, a cubic equation, and if I can solve this cubic equation, then I will get the unknown value of B. So, this problem actually what I can do, I can consider F B actually. F B is nothing but B cube plus 16.4 B square minus 52.5. and I have to find out, I can assume different values of B and try to find out f b value, and f b value has to be 0, this has to be 0. So, that means I can nowadays actually there is a equation solver. If I put in the equation type and those coefficient, I can find out by single step the value of B, but in the examination hall you will not get that type of calculator, that is where equation solver will be there. What I can do? I can assume different values of B and try to find out the f b value, and when the f b value will be become close to 0, then that is the value of B for the actual value of B. So, how to then choose the value, initial value of B? The footing size generally vary from 1.5 to 2.5. So, approximately you can assume first the B value is 2, then you can find out the B, using B value of 2, then you can find out that this value f b value, it is not equal to 0, it is something value greater than 0. So, like that if I find the positive value, then B value you can reduce, if I value large negative value you can increase the value of B, like that trial and error method you can do. And finally, if I use B equal to 1.7, if I use B equal to 1.7 in this equation, B equal to 1.7 in this equation, I get f b close to 0, that is equal to minus 0.1 actually, I am getting minus f b equal to minus 0.1. So, that can be considered as well close to 0. So, that means I can assume different values of B and then find out the f b, and when I find the f b value is close to 0, that means that is the value actually B is correct. So, by using B equal to 1.7, we are getting f b value close to 0, that means that B actually is the correct B of this equation. So, that means from this equation finally, I get the width of the footing required actually equal to B of the footing required is 1.7 meter by 1.7 meter. So, for this problem the solution is that when the footing is placed at 1.2 meter depth and it carries a load of 2500 kilonewton, and the soil is with phi equal to 30 degrees and C equal to 38.3 kilonewton per meter square, this is kilonewton per meter square, and gamma is 18.5. For that situation the required footing size is 1.7 meter by 1.7 meter. So, this is the procedure for solving this problem. I hope it is clear enough. I will take some more problem also later on. So, what I have to do? I have to do first Q ultimate, from Q ultimate I have to find out net ultimate, from net ultimate I have to find out net allowable multiplied by the area of the foundation become the load, and that load should be compared with the given load, that is done here. And if you do, then I will get a cubic equation here, and if I solve the cubic equation, how to solve the cubic equation? Assume a trial value of B and try to find out the value of the function close to 0. When value of the function become close to 0, that assumed value of B is the width of the footing, actual width of the footing. So, by that actually I have got B equal to 1.7 meter, that means since it is proposed a square footing, that means size of the footing is 1.7 meter by 1.7 meter. With this I will just close here. Thank you.